Anyway, this is an introduction to optimization. So let's just write that up here. First, can you guys see this screen?
Yes.
Okay. And I'm going to share the link to this in the chat. And so as we're going along, if you guys have things you want to point out or add or whatever, you have access to that. You can write directly on this whiteboard. And when we talk about optimization here, what we're talking about is how do we get a computer to solve this problem, right? So how do we figure out how to teach a computer to solve an optimization problem? There are ways that humans could do it if we had a whole lot of information available to us, but how do we get a computer that has limited information? How do we give that computer the ability to solve this problem? So I'd like to just start off with questions. I'd like to know what you guys are hoping to get out of this workshop in the next 2 days. And feel free to drop those in the chat or unmute yourself and just mention it.
I have some experience with optimization algorithms. I'm more new to like the concept of multiprocessing and things like that to solve the optimization problem. So I'm not sure if we'll get into that too much.
Okay.
But that's the issues I'm running into with optics right now.
Okay. Okay, so I'm just going to make a note here. So for multiprocessing.
And if that's a little bit like for another video as well, that's
okay.
fine.
Okay, we may or may not get there, but we'll try. Yeah.
I feel like I got a lot of like experience optimizing things in classes, but I had to learn things on the go or like just as we did it instead of getting like foundation with optimization. So I kind of took classes in a reverse order, where this fall I'll be taking optimization for engineers, where I've had to use optimization methods without getting it like a good foundation for them.
Okay. All right, great.
One more thing is time to solve the problem, like between different methods and some of the benefits and when to use them would be good.
Okay.
I think similar to Nolan, I've never done optimization before. Well, I guess not similar to Nolan in that respect, but doing optimization this year for the lab challenge kind of opened up my eyes a little bit, and so I'm hoping to just get a more basic understanding, I think, of optimization and its uses.
Okay.
I also would be interested in learning more like debugging techniques with optimization, because sometimes I'm not sure what's going on under the hood, and so I don't know how to what could be going wrong.
Okay. Yeah, that's a great question. Good question. Okay, and then in the chat, the only exposure I've had with optimization is a brief touch on it in numerical methods and our lab challenge. So I'm just hoping to have as much exposure as possible at this point. Okay, great. So we'll just put some exposure / experience with it. Okay.
If I could add something, this maybe goes along with how to debug, but I'd like to know if there are any tips or tricks for helping optimization algorithms converge.
Okay.
Particularly like when you're close to an optimum, but you get your result out and you're like, okay, that's not quite optimum. Like you can tell. Anyway, so some insight there might be nice.
Okay, great. Okay, we will do our best here. These are a lot of exciting questions. So I'll do my best to cover, as much of this as possible. And again, I should probably make a little bit of a disclaimer here. You guys know that optimization is not my my area of research or my forte, so to speak. I've worked with it for many years. I've taken at least one. I don't know if I've had more than one class on it, but that class I thought was very well taught, especially from an application standpoint. And so I learned a lot through that process. And so anyway, I'm just going to share what I understand and the edges of my understanding. And there are parts here that obviously I'm not well versed at. And so we'll just kind of do our best as we work through this. Okay, so let's start off with some definitions and terminology. All right, so I guess maybe the first one is optimization. What are we trying to do when we're talking about optimization? How would you define optimization?
For me, it helps to think about it graphically. If you're going to have a parabola or a function,
Okay.
you're going to try to find the place, like the minimum, like where the minimum value in the y location. It would be on a parabola. That
Okay.
dip. So you're going to try to find a certain point where a function is a minimum value, or if it was an upside down parabola, the maximum point you could possibly reach within a function. If
Okay.
that makes sense.
Okay, so let's say we have a parameter here that's a function of just a single input variable x, right? That's our independent variable x, and we have some y coming out of this. So this is a function, and we want to find the value of x that minimizes y, right? So that's a very simple explanation of optimization. You're trying to find the x, we're going to look at it as even a vector, or an array of inputs instead of a single input, but it's easy to visualize it if it was just a single input. So we're going to be looking at, what's the collection of input variables here? If we have maybe 5 different things that go into this system, what's the best combination of those variables that gives us a specific output? And in this case, usually when we are formulating an optimization problem, we put it in terms of minimization instead of maximization, okay? And that doesn't really matter, except that that's just kind of a standard that was adopted. So we usually formulate our problem. All of these optimization algorithms that we're talking about are set up to minimize rather than to maximize. And there are some benefits to that. So for example, what if I, it's easy to visualize here with this parabola, and let's just say for a second that we had a parabola, that looked like this, and we were trying to find the maximum of that parabola. Well, we can reformulate that problem by just passing in the negative, or when it comes out, we can just flip the sign on that function and still have our optimization code work with this, try to find the minimum instead. Does that make sense? We can just flip the sign on the function here.
And Dr. Hunsaker, I don't know if I'm getting too cut up, like just if this is for videos for people trying to learn, the way it was kind of laid out is just for the stability of the algorithm. If you were to imagine a ball sitting on each function, in the minimization function, it's going to converge and be stable. Whereas if you were to set it on the reverse parabola that you have in red, it's possible for that ball to go off to one side. It's not a stable function. If you were to look at it as trying to maximize it, if that makes sense.
I can see what you're saying. I'm not sure if I agree with that totally.
Okay, that was just, okay.
I'm not sure if I agree, but let's take the ball analogy here for just a second. So as we're trying to minimize this function, you can imagine this ball, and we're going to test out different things and allow it to roll downhill until it finds this minimum point, right? So I guess the only reason that analogy would work is if there's some kind of force on this ball that's pulling it down. And I guess the same, we could imagine a maximization having a ball over here that's going to move in this direction until it finds the maximum up here. But there's no theoretical force that's pulling it away from there.
Nope.
So
You're-
anyway, you may have an analogy that I haven't heard of before, or that does hold water. I'm not seeing it immediately.
Okay, I'll let you continue. Sorry.
But let me explain one reason it is advantageous to minimize instead of maximize, and that is because what if on this function we wanted to find the x location that gave us a specific value instead of the minimum? So rather than trying to find the minimum of this function right there, what if we wanted to find the location, and there happen to be two on here that give us this specific value? So we would be looking for a combination that gives us that point or this point over here. Does that make sense? So it's simple, again, to reformulate this problem in terms of a minimization problem, because we can take this function and subtract off the value that we're looking at. Let's say that it was 5 here. We could subtract off the value of 5, and now we've recreated or we've created a new function that is going to be 0 at those 2 points. And so if we want to, then we could minimize the absolute value of that new function. Basically, our old function -5, we could minimize the absolute value of that. And again, that would create 2 new minimums here, one at this point and one at that point, where they cross the x-axis, basically, right? Where the y value is 0. And so we could minimize the absolute value of that. So anyway, there are some benefits to minimization over maximization, and that's just kind of a standard. So you should just be familiar with that pretty much all optimization, all those algorithms are trying to minimize rather than maximize. Okay, we've touched on a couple other definitions here in the process, and let's just formally write them down here. So we have things called design variables. And this is this X right here is a design, these are the design variables. And if there's only one, then that's singular, it's a design variable, but we could have a whole array of these, and you can have as many as you want. There are very complicated functions that have a whole lot of design variables coming into them. And then, and those are also sometimes called the degrees of freedom, okay? Because that's how many knobs, so to speak, you have to manipulate this. So degrees of freedom. So that's kind of the degrees of freedom of the system. Okay, we're also going to have a concept of a design space. Okay, so a design space is basically, again, in one dimension, this is easy to visualize, but basically our design space would be, it can have a certain width here or a certain range of input variables that are allowed from this X vector, and it can have a certain range of outputs from our Y variable, or our dependent variable. And so this concept of a design space is really important, because sometimes you'll have a function that once you leave that design space, it might go haywire out here, and we're really looking for a solution in a certain region. And so that region we would consider, this is the design space. We're gonna kind of put a box around this area. This is the area that we're interested in. Where if that design space was much larger, if we did consider values out into these regions, then the optimization problem may become more complicated, or maybe there's more than one solution, or a lot of different things like that. So anyway, the design space is just simply the domain and range in terms of functions. The how large of, or what's your domain on X's, what's the range of appropriate input parameters and what's the range of output parameters that you would get from that. In design spaces, we're going to try to visualize some today in higher dimensions. This first one is just a one-dimensional example. That's really quite simple to visualize. But once you get up to higher dimensions, if you have, for example, 4 input variables, if your X array has 4 components, then your design space gets a lot more complex to be able to visualize, and so we'll talk about how to do that here a little bit later on. Okay, and then finally, one last thing is what's called an objective. And this is often called an objective function, but the objective is, for us, it's this Y value up here. So the objective is, what's the component coming out of this that we are trying to, or the dependent variable that we're trying to optimize on, what's that final value? And so this is Y up here is called the objective. And we are always trying to minimize that objective or that objective function, okay? Okay, so those are just some terminology we're going to be bouncing around today as we work through some problems here. Okay, so let's start off with an example problem. And what I'd like you to do is pull up Excel. We're going to use Excel today quite a bit. And the reason I like to use Excel is because it allows you to visualize more easily what's going on. I know eventually many of you are going to go to Python or other codes or whatnot to solve these things, but for basic understanding, it's really helpful to start in a spreadsheet setting. And so what I'd like you to do, so we're going to call this exercise 1. Exercise 1, I would like you to use the function, let's see, actually, we're gonna use this function, z equals x squared plus y squared. Okay, so there's our function. We've got 2 input variables, and actually another way that you'll often see this written is z equals x1 squared plus x2 squared. Okay, so we have 2 input variables here. We have x and y, and let's just draw out what's going on here. So we've got x and y, those are our input variables. They're going to go into some function, and out of that comes a variable that we call z in this case. Okay, so x and y are the design variables, and then we've got some function or model, some system that's going to go through. And then out comes the z. This is the objective on the right-hand side. Okay, so in our case, we've got this x and y coming in. We've got z coming out. And so what I'd like you to do is, and I'm going to work through this with you, is to visualize this design space using Excel. Okay, so let me pull up Excel here. And by the way, I'd really like you to work through this with me if you have access to Excel. Okay, so how are we going to visualize this design space? You probably know how to do this in one dimension. So for example, what if we had the function, z equals x squared, for example, right? So I'd have a column of x's, oops, there we go, x's, and I'd have a column of z's, and this x, let's say we're going to go from -10. We'd have to, again, choose the range of numbers that we want to look at. I'm going to go from -10 to +10 here, and z is equal to x squared, right? And so that's you've all done that before. This is just a real simple function. And so then we can insert a plot here. So this is Z as a function of X, or usually we would use Y. If there's only one input variable X, then we would call that Y as a function of X. So you guys are all familiar with how to visualize this, right? But how do we visualize 2 dimensions? So we've got now, we're gonna have an X column, and I'm actually now going to add a Y column or a Y row going this direction. So again, I'm going to use -10, -9. By the way, let me just delete this so it's not confusing here for a second. So I've got an X column in this dimension, and then going across to the right, I'm going to add Y, and I'm going to use the same range on that. So from -10 to +10. Okay, so we've got our 2 inputs, and now at any cell in here, I'm going to use the corresponding X and Y inputs there to tell me what the value is at that point. So let me just put these in bold so we can kind of see those, and I'm actually going to shorten this up a little bit so we can, okay. Okay, so we said this is our function down here. So it's X squared plus Y squared is Z. So I'm going to put in a Z value in each of these cells. So this is equal to X squared plus that Y squared, right? And then I could come over to this guy and I could say, well, that's equal to this X squared plus that Y squared, right? So I could manually fill in every cell in here. Now Excel has a nice option for automatically filling all of that in if I just tell it which of these I want to hold constant. So for all of the A column information, I always want to be working in column A. So I'm going to put a $sign in front of A. And then for all of the B, all of the stuff in row 2, I want to keep row 2 the same everywhere. So I'm going to put a $sign for that value there. And so now I can just drag this over and copy it down. And so now I can, let me just double click on this and make sure it's using the correct input. So it's using X there and Y there, right? Okay, so now I have a value for every single one of these X and Y inputs. Any questions before we move on of how we did this? Everyone feels comfortable with Excel to this point? Okay, so now let's try to visualize this design space. Now you can do it kind of manually. You know, you can see, oh, there's kind of some big numbers over here. They seem to be getting smaller as we move in towards the center. And obviously, you know, the solution, and maybe you already knew this in your head, the way to minimize this is if X is 0 and Y is 0, right? That's how we get the minimum here. But maybe, you know, sometimes we don't know this function is so complex that we can't just look at an equation and know exactly how to minimize it. So I want to be able to visualize some things here. So anyway, we can see that 0 there right in the center with the 0 inputs. That's obviously the minimum. But how do we visualize this? Well, let's select that whole thing, and then I'm going to go to Insert. And there's a kind of a plot here called a surface plot, and I haven't played around with these a whole lot. I'm gonna try this guy. There we go. There's a surface plot of this design space. So this is a two-dimensional. This is really a three-dimensional design space, and these are fairly simple to visualize because we have 2 inputs. We've got an input along the x-axis, we have an input along the y-axis, and then we have a z-axis output. Okay, so by the way that we've selected this, Excel didn't know that these are the values here along the x-axis and the y-axis, and so it said, well, I'm just going to call these 1 through 21. We had 21 inputs over here. And then we're going to call these series 1 through 21 on the Y stuff here. So anyway, so don't worry about the labeling here. You could do some modifications here to get these axes so that they actually had the values along here. So it would go from -10 to 10 on the x-axis, -10 to 10 on the y-axis, and then we'd see the z output. So, so you might notice that this, kind of looks like a hammock or something. And so we would be looking for what's the value that minimizes or the number that or the inputs, the x and y inputs that give us the minimum z output. Another way to think about this is like a mountain range. Okay, so this design
Okay,
space.
Victor, I missed where you found the contour plot.
Okay.
Because it took me a minute to get the data, just so I can
Okay.
follow along with you.
Yeah, so you just select this set of data.
Mhm.
And then go to insert, and I'm on a Mac. I believe that on the most recent version of Windows, if you're on Windows and using Excel,
Oh, is this? I found it now.
I think it might look like a spider plot thing. The graphics might be a little different. I'm not sure. Maybe that's an older version of Windows. I'm not sure. But anyway, this is what we're looking for. These are surface plots. I think like the little icon up here on some versions of Windows looks something more like this. But anyway, so we can do what's that?
I said, thank you. I found it
You
there.
got it. Okay. So the one that we chose was a 3D surface, but we could also do a contour. So this would be like a top-down view of that design space. And actually, this is the way that we usually look at three-dimensional design spaces, where we have two inputs and one output. So we have an x-axis and a y-axis, and then the z value, we often have it set as a contour, meaning that the lines along here or the breaks along here are points that have all the same value. Okay, that's what a contour plot is, where the lines along here are lines of constant value, so constant z output. And so you can see that this design space looks like, they actually call this a spherical design space, I believe, where basically we move in on that optimum in a perfect sphere. Okay. Okay, so the point of today is to or of the next 2 days is to better understand like what types of design spaces, what these might look like, these top-down views, and how would we teach a computer now to find the X and Y inputs that give us the very minimum here, right? Okay, any questions on this example before we move on? All right, so let's talk about a couple requirements for optimization here real quick. Let's see if I can move this over here. Okay, so we have a couple requirements that you probably just should be familiar with in order to use a computer-based optimization method. Okay, so let's just write these down. We've got some, and I'm just going to list two today. There might be more, but these are the two main ones that I'm aware of. Number one, our problem here must be some kind of a function. Okay, meaning that for my given set of x's, so my x array or my set of inputs here, they always give me the same output. If I put in that same collection of x's, I'll always get the same output. Now, so I'm just going to say that x gives me a certain z. Okay, for example. So another way to say this is that it's deterministic, meaning it doesn't matter if I put those in today or tomorrow or next week. If I put in that same collection of x values, I'll always get out the same Z value. And this is kind of important because if that's not the case, then every time I called my function and put in those X's, if I got a different Z value out, you know, that's not a deterministic function. And there is really no way for the optimization code to be able to tell if it's progressing toward a solution or away from a solution, right? And even us as humans, if every time we put in something into this function, we got something different out, that would be a problem. Now, there's one caveat to this, and that is that sometimes you have a little bit of numerical error or a little bit of error in that value that might be slightly different every time you call that function. So for example, and actually that already happens even with this example over here. You know, Excel is computing these values probably out to 16 digits of accuracy, you know, using double precision. But what if we were looking at 18 digits of that solution instead of 16 digits? Those last few digits would probably be different every time we updated that cell, because those last few digits are just numerical noise that come out of the operating system, because it really only can track so many digits of accuracy, right? So we already deal with that to a certain degree, where no matter how good your setup is, you're going to deal with a little bit of error in that solution that comes out. And so that's very important to recognize later on when we talk about gradients, because when we try to compute the difference between two solutions, we're going to look at, you know, here's a set of X inputs, here's a set of X inputs, and we're going to look at the difference in Z that comes out for each of those inputs. You know, if you're trying to compute gradients that are on the order of machine precision, you're just going to get noise, right? Numerical noise. So anyway, so this is an important point, though, that basically the function is deterministic. That actually is the definition of a function, right? Or a function, and we've always thought of it probably in this two-dimensional form up here, where if given any X value, you only get a single Y value. Remember, if this curve ever wrapped back on itself, and for a single X input, we could get two different Y values, that's not a function anymore, right? That's not a deterministic function. Okay, so that's one requirement. And then the second requirement is basically that the output has to be quantitative. Okay, meaning that we can really only work in a numerical space here. You know, so, you know, what are some things that wouldn't be numerical? You know, we're always in our lab, we're always doing things with numerics. So this is a little bit of an abstract concept here, but what if you were trying to optimize something and figure out which combination gave you something that was most red, right? Well, we'd have to formulate that in terms of a quantitative output. And so we'd use RGB values or CMYK values or whatever, you know. This is how we tell whether or not this is red. It's got to be a numerical output that tells us how close we are to a solution. So anyway, and that's, like I said, that's basically everything we do in our lab is all numerical. So that's kind of a moot point. But just so you know, I'm not aware of any way to do optimization if your output isn't quantitative, if it's qualitative instead of quantitative. Okay. Let's just draw here a real simple, I kind of alluded to this earlier, but I'm gonna just draw a very simple schematic of every optimization problem, okay? So we have inputs, these are our design variables. Okay, so we have a collection of design variables, inputs, degrees of freedom. You know, these are the things that go into our system. Those are going to go into something that we call a model or a function or a system. Okay, so those are the inputs. They come into this thing, and then out of this comes the output. And to start with, we're only going to look at cases today where we have a single output. Okay, tomorrow we'll talk about what if we have more than one output and we care about both of these outputs. We'll talk about that a little bit more. But today we're going to talk about just the case where we have a single output. And again, some other words for this are the objective. Yeah, I think that's it. Any other thing that you guys have heard that called?
In the case of like tomorrow with multi-objective, it would be multi-objective.
Right.
They should-
Multi-objective optimization. Yep.
You have two outputs. Okay.
Yep. And there's another scenario here where we have more than one output, and we're still trying to only optimize on one output, but we want to make sure that the other output doesn't step out of bounds, or that the other output is still. So, for example, in your case, Nolan, you have these collection of inputs, and you want to make sure that you're trying to minimize PLDB, but you want to make sure that the area of your geometry doesn't go negative, right? So that's another output of does this area ever go negative? That's another output that we want to make sure doesn't ever go negative, right? We always want to be working with positive. So we would call that a constraint, where we're gonna tie some of the outputs, instead of trying to minimize them, we're going to constrain them to make sure that they don't step out of bounds. Okay.
Okay.
Okay, so let's actually just talk about that for a second. So if we may have limitations on these X values. So the limitations on the inputs, we call those bounds. We say, our X value in this case over here, and this is really arbitrary, but I might have said, well, my X or Y values can't leave this region between -10 and +10. That's a bound, okay? And then limitations on the output on other outputs would be constraints. So again, there can be many outputs over here. There can be many things that are coming out of this, but today we're only going to talk about a single objective, okay? Meaning that we're trying to minimize one of those outputs. But the other outputs, we might have limitations on those, and we call those constraints. Okay, so this is basically what every problem looks like, and our job today is to say, okay, how do we wrap and some kind of optimization algorithm around this? How do we solve this so that we could take the outputs here, pass it into some optimization algorithm, and it could tell us what the next guess should be on our inputs to get closer to the minimum, right? So this optimization algorithm here is really going to be the discussion, what we're talking about today. How do we use the stuff above here? If we already have this system set up where we have inputs, a model, and an output, how do we make some algorithm over here that's smart enough to figure out, okay, if I change the inputs like this, this is how the output's going to change. How do I keep getting closer and closer to that minimum point, right? So that's what we're going to be talking about. How do we teach the computer to do that? Okay, before we move on, there's some things that I'd like to introduce you to. Two more terms, really. So here's some new terms here. And these two terms are local optimum and global optimum. Okay, and to understand this, we're going to look at a Wikipedia page that actually Corey sent me. Let me drop this Wikipedia page in the chat in case you'd like to archive it or pull it up or whatever. These are test functions for optimization. We're just going to kind of try to kind of orient ourselves on this page here for a minute, okay? So when you come up with a new algorithm, there's no single algorithm we're going to find. Every algorithm has pros and cons, things that it's really good at, things that it's not very good at. And so there's no one single algorithm that's just our best optimization algorithm out there, okay? As much as you know, it'd be nice if it were otherwise, where we could just type in SciPy to optimize and it would just solve the problem, right? There's too much complication in how to solve these things, what the design spaces look like. There's just too much going on there to have one big global algorithm that can just solve every problem perfectly, okay? So really what we have is a bunch of algorithms that people come up with over time, different ways to solve this, and we're going to go over a few of those today. But in order to understand why some are good and why some are not so good, we need to understand what the design space may look like, and what different design spaces kind of look like. And so here's a bunch of preset design spaces that people have developed that actually, let's start with this one here. This is the sphere function. We've actually just done this one already this morning. So the function here, f of x, and x is bolded here because that's a vector, is equal to the summation of the number of x's you have, each of those squared, right? So this is just, you know, x1 squared plus x2 squared plus x3 squared. You can have as many inputs as you want here. We only looked at two inputs, x and y, or x1 and x2. But anyway, this is the function that we just looked at here today with just two inputs. And you could have as many inputs as you want. And the design space would still take on this kind of a nature here. Okay, so let's just, this is the formula. This is the global minimum, is that all of the x's, all of the inputs are 0, right? And the solution is also 0. So we saw that earlier, that's the solution to this problem, is that all of the inputs go to 0. And what's the search domain? Well, you can search from negative infinity to positive infinity, and from in any value of x, and this can be from 1 to n, where I think n can be infinite as well. You know, you can add as many terms here, and it's really not going to change what this design space looks like. So this is the sphere function. We've visualized it. Again, this is that same function right here. We visualized it in 2 dimensions, where we had an x and a y input, and then the z we put in contours. And so you can see that's exactly what we're visualizing here. In fact, they've called it x here along the x-axis. They go from -2 to 2, and then on the y they go from -2 to 2. So this is rather simple to visualize a you know, 2-dimensional design space where I have 2 inputs, 1 output, because we can look at that in a contour plot. So all of these, this is how we're visualizing all of these, as even though they can have many more dimensions inside of them, okay? But so these can also be considered a slice of the domain space. So for example, what if we had 3 inputs over here? Well, this would be the slice of the domain where the 3rd input is 0. Right? This would be a 2-dimensional slice through that domain. A 3-dimensional domain would actually look like a Rubik's Cube, where you can have X, Y, and Z inputs, and then you could visualize the output value as, or the function as a heat map within that Rubik's Cube. And so you can imagine now that we've just sliced through that Rubik's Cube, where the 3rd dimension, we've sliced it at 0. So through the center of that Rubik's Cube, this is what the heat map would look like in there. And we're trying to find the coldest point inside of here. We're trying to find the minimum value, right? This would be a slice through that domain. Can you guys visualize that, what I'm talking about? Yay, thank you. Yep, that's a Rubik's Cube right there for you. So anyway, above 3 dimensions, above 3 inputs, well, when we're visualizing things, it's really nice to take a 2-dimensional slice through any domain, and that gives us a really good idea of what this domain looks like, right? above 3 dimensions, it's very challenging to visualize. Our human minds are challenged. You know, we can't really imagine 4 inputs to something. How do we visualize that? Well, the next thing up would be, what if that Rubik's Cube, what if the heat map inside of that were changing with time? Well, we can look at it in one instance in time, and we can take a 2-dimensional slice through that Rubik's Cube. And again, we'd come back with something like this, but now that 4th dimension would be basically, what if this was changing with time? And we wanted to find the time that minimized that value as well. So anyway, and you can go up in further dimensions from there. But anyway, it's really challenging for us as humans to visualize higher dimensions. And so usually the way we visualize those is just with the 2-dimensional slice, where we look at 2 inputs and assume that the others are all 0, okay? Or some constant value, I guess I should say. Okay, well, you can see that some of these design spaces can get kind of nasty, right? So let's look at this one here. And I don't know how to pronounce this, Rastrigini function. Oh, look at this. If you hover over it, it will kind of flip that on its side and show you a, you know, the mountain view here instead of the contour view, but the 3-dimensional view. So you can see what that looks like. So we've got a lot of local minima. Okay, so little places where all around it, everything goes uphill. And I'm not sure if you guys can see this very well. Let me see if I can zoom in just a little bit. Yeah, this might help a little bit. Okay, so each of these blue dots here, we would call a local minimum. Okay, that means that if you were to cut the design space around that region, that's the minimum. Everything goes uphill from this point, right? So if you visualize this as a mountain range, if you were hiking around in this mountain range, you might have a little lake or something down there where the water has collected, right? And if you couldn't see very, very far outside of this, you would believe that you were at the minimum, right? Everything goes uphill from here, right? At least in the vicinity directly around that point, everything is uphill. So we call that a local minimum. However, it may not be the global minimum. There may be another point in this design space that has a lower value, but you wouldn't know it unless you could get outside of this valley somehow and look further, you know, beyond the mountain ranges that surrounded you. So the global minimum here is at this red point here. And again, the global minimum is 0, 0. And you guys might be thinking, well, these are trivial solutions. You know, why wouldn't you just know that it's 0, 0? Well, the point is that we're going to not tell the optimization algorithm that it's 0, 0. And this is one way to test an optimization algorithm. We say, let's start over here with a guess of -4 and -4 or something, you know, over at this point. Can you find the global minimum? You know, we give the algorithm those kinds of challenges to see how good it is at finding the global minimum or local minimum. And we're going to find that there are some solutions that are excellent at finding local minima, but really poor at finding global minima. And then we're going to find that there are other methods that are really good at finding global minima, but very slow at finding local minima. So anyway, so we'll talk about a few different ones here today. So you can code this up. I'll leave this as an exercise to you guys. If you want to code this up in Python or in Excel or something, you can easily create these design spaces to look at. Okay, here's another design space. This is kind of interesting because again, we have some local minima. You know, every time you have a ring, that basically means that there's going to be a minimum or a maximum inside of that ring, because these rings are regions of constant value. And so that means that inside of this ring, there's either a peak or a valley, okay? But along the surface of that ring, it all has the exact same altitude, so to speak, right? So again, we have a single global minimum here at 0, 0. And again, we're only visualizing this in 2 dimensions. In fact, this one is only a 2-dimensional function. This one is a multi-dimensional function. We're only looking at a slice, you know, in that where it could have 3, 4, or an infinite number of dimensions, I believe. Okay, here's some more interesting ones. So this kind of looks like a cavern here. And maybe if we, no, it's not going to show us a 3D rendering of it, but here's our global minimum over here. And you can imagine that this is like a canyon of sorts, right? If we started over here, or maybe if we started up here on the hilltop, we might walk down here to the bottom of this ravine, but then the ravine slowly moves downhill. And so we might, you know, if we were hiking and just trying to find the minimum, we would kind of hike around here until we hit some point where at this point, everything is uphill, right? So, you know, how are we going to make an optimization algorithm? It could, if it just always wanted to walk downhill and we started it up here, it might walk down to this and then take a really long time to walk around here and find that point. Is there a faster way to get there, right? These are the types of things that you try with these optimization algorithms. Okay, well, I'm not going to belabor this much more, but you guys can see, you can just scan through. There's all different types of design spaces, and you should be aware that your design space, again, we're only looking at a two-dimensional slice of this. Your design space is probably many more dimensions in, you know, you have many more inputs here. And so it's really challenging to visualize this, but if you can get slices of your design space, then you can start to understand what kind of problems your optimization algorithm is up against. You know, how is it going to find that? And is it going to find it? Is it going to be really, really challenging for it to find? Or do we have a whole bunch of local minima, or is there only one single global minimum? And, you know, all different things about your design space are really helpful to understand before you choose the type of algorithm that you're going to use to solve this problem. Okay. So I want to pause for questions here. What are your thoughts and questions so far? Nothing? Okay, then I would like to have you run an exercise here. We're going to take about 10 minutes, all right? I would like you to choose one of these functions. Again, I dropped the link in the chat. I'd like you to choose one of these functions, and it can be one that has as many dimensions as you want, but only make it a function of 2 inputs. I'd like you to put this into Excel and visualize the design space in Excel. Okay. So again, choose any of these functions and simply try to visualize a slice of this domain space in Excel in 2D. Okay, so I want to see a contour plot, something like this. And we'll take about a 10-minute break here for you to work on that. We'll leave Zoom running. So if you have any questions or anything, you know, you can just speak up or drop it in the chat. And anyway, we'll just take 10 minutes here and then reconvene.